You see it every single day. I mean, it's literally the foundation of our cities, right? It's in the walls of our homes, the bridges we cross. But what if I told you that inside this totally familiar gray stuff, there's a hidden universe, a secret life that decides whether a skyscraper stands for a century or a bridge just crumbles under pressure? Well, today, we're going to peel back that surface and take a look inside. We're going to explore the secret life of cement.
So that brings up a pretty big question. How on earth do you see inside stone? I mean, really think about that. To understand what makes concrete strong, or durable, or maybe even greener, we have to become microscopic detectives. We've got to find a way to peer inside what looks like solid rock.
And this just shows you the scale of the challenge we're up against. We see these massive, giant structures, but the real story, the chemical reactions, the way crystals grow, the teeny tiny flaws, that's all happening at a scale that is thousands of times smaller than a single human hair. It is literally a universe hidden in plain sight.
Okay, so our first stop on this journey is to really wrap our heads around this hidden universe. It's this incredible world where the absolute tiniest structures dictate the mightiest outcomes. And getting this right, well, that's the difference between real innovation and just failure. And believe me, the stakes could not be higher. We all want buildings that last longer, right? We want to use materials that are less carbon intensive, and we need structures that can stand up to harsher and harsher environments. So, to engineer that future, we first have to be able to see it at the microscopic level.
So, how do we do it? How do we peek inside? Well, we need a special kind of eye. Not one that uses light, like our eyes, but something way, way more powerful. And that's where the electron microscope comes in. This thing is our super eye, the scanning electron microscope, or SEM for short. Now, I want you to forget everything you remember about those microscopes from high school biology class. The SEM doesn't use light at all. Instead, it shoots a high-energy beam of electrons to scan a material and see what's really going on inside. But wait, how does shooting electrons at a piece of stone actually let you see anything? Well, it's all about the signals it creates.
Okay, so as that electron beam hits our sample, it actually creates this whole shower of different signals. You can think of it like a detective's flashlight hitting a crime scene. It doesn't just light things up. It actually reveals all different kinds of evidence depending on what it hits.
And those signals, they are everything. They're the clues that tell us what the material is made of, what its texture is like, and how all its different ingredients are arranged. So, here's the crucial point. We have our tool. Now, we need our evidence.
And this is where the science really becomes an art form. You see, you can have the most powerful microscope in the entire world, but if your evidence, the sample, is messed up or poorly prepared, all those clues become totally useless. The scientists who wrote our source material said something that really says it all. They said, electron microscopy is probably the most widely misused technique in cement science. That's a huge statement. It tells you just how easy it is to get a pretty picture, but how incredibly hard it is to get a truthful one. So the truth isn't just hiding in the microscope, it's in the absolutely painstaking preparation. Any little mistake can create what are called artifacts, features that look totally real, but are actually just a result of the prep process itself. It's kind of like finding fingerprints at a crime scene that belong to the detective, not the suspect. And the process itself is unbelievably precise. First, scientists have to freeze the chemical reactions right in their tracks. Then, they infuse the sample with a special resin to support its delicate internal structure. After that, they have to polish it, sometimes for hours, to get a perfectly flat, mirror-like surface. And finally, they coat the whole thing with a thin layer of carbon so the electron beam can actually scan it. Every single step is designed to eliminate errors and reveal the truth. And just look at the payoff here. On the left, you see a beautifully polished sample. You can clearly tell the different components apart. It's crisp, it's clear. Now look at the right. It's a disaster. The surface is all chewed up, the features are blurry, the clues are completely gone. This is why the prep work is the whole shebang. So, with our perfectly prepared sample sitting inside our super eye, what do we actually see? Well, the microscope gives us two different kinds of clues, two really different ways of looking at all that evidence. So, we're mainly looking at two types of signals. First, we've got secondary electrons, or SE. These give us the topography, the physical shape of our microscopic landscape. Then we have backscattered electrons, or BSE, which tell us about the chemistry, the actual identity of the materials we're looking at. Here's a really simple way to think about it.
The SC image, that's like a stunning black and white photograph of a mountain range. It shows you all the peaks, all the valleys, all the texture. But the BSC image, that's like a full-color geological map of that same range. It tells you which parts are granite, which are limestone, and which are shale. One shows the shape, the other shows the identity.
Let's look at a real example to see what I mean. On the left, that's an SE image showing this beautiful, complex texture on a fracture surface. It's all about the physical shape. But now look at the image on the right. That's a BSC image from a polish sample. Those different shades of gray aren't random. They're revealing the chemistry. See, heavier atoms are better at reflecting electrons, so they show up brighter. This lets us immediately tell the bright, unreacted cement grains from the darker gray stuff, which are the new compounds that actually give concrete its strength.
But, there is a catch. We're getting these incredible, detailed maps, but they're flat. Every single image is just a two-dimensional slice of a deeply complex three-dimensional reality. So it's a fantastic clue, for sure, but it's not the whole story.
So you might be asking, why go through all this trouble? Why do all this work? Because even these 2D clues are enough to start building the blueprints for the future of construction. You see, by piecing all this evidence together, scientists aren't just, satisfying their own curiosity. They're solving real-world problems. Everything from making concrete greener to figuring out exactly why a structure failed. For example, by watching exactly how new, blended cements react at this micro level, engineers can design materials that are way stronger and have a much smaller carbon footprint. What you're looking at here shows precisely how different components are interacting to form this dense, durable material. We can also use this to make our concrete way greener. This image shows fly ash, which is a waste product from coal plants being used inside cement. The SEM lets scientists measure exactly how much of that fly ash is actually reacting and contributing to the strength. We are literally turning waste into a valuable resource. And finally, this brings us full circle right back to our detective story. When a structure fails, the SEM is the ultimate forensic tool. This image here is an elemental map. The investigators have colored it to show how damaging sulfates, in red, have invaded the concrete. You can literally see the path of destruction, which allows scientists to figure out what went wrong and, more importantly, how to stop it from ever happening again. From the most mundane things to the most magnificent, our world is built on materials whose true nature is totally hidden from our eyes. By learning how to look inside stone, we've unlocked a universe of possibilities. And it really makes you wonder, what other everyday materials have a secret life that we're only just beginning to understand?